So remember, um, the graph of y equals 1 over x. X is not x equals 0, is not a point in the domain of this function reciprocal. When we draw the graph of this function, the graph looks like this, right? So x equals 0 for y-axis. X equals 0 is the Cartesian equation of the y-axis. So here we have even though 0 is not in the domain, we can still talk about what happens as we approach to 0. Um, so we can say if we go to 0 from the right hand side, when we go to 0 from the right hand side, function values goes to infinity, positive infinity to be precise. Then what happens as we go to negative infinity is a little bit different. When we go to 0 from the negative direction or left hand side. Now function values are decreasing with no lower bound. They decrease and decrease and decrease. It keeps decreasing with no lower bound. So it goes to minus it. And let's see what happens for very large x values. To see what happens for very large x values, let's take some large x value, let's say something here, and see what happens beyond this point. So here x goes to infinity and function values are decreasing and reaching to 0. See, this part over here, um, um, the function values are decreasing and reaching to 0, but it never becomes 0. So it is kind of interesting thing. So as x goes to infinity, y values are reaching to 0. The same thing happens for very large negative numbers. When we go to negative infinity, again function values are now increasing up to 0. Function values are increasing up to 0. So this thing happens for uh, this thing happens as x goes to positive infinity. Also, it happens as x goes to negative infinity. So here something interesting happens as x goes to positive infinity or negative infinity. Y values are reaching to a finite number. This is finite. Let's say this happens. Now let's see the general picture. Suppose for y equals our function f of x. We have x goes to positive infinity, f of x equals some number m. Now, on the graph, it will reflect something like this. So we don't know anything about the anything about the function, but we know as x becomes very large, function values are reaching to some number m. So here, this is the line y equals m. Now, I don't know what happens. As x goes to positive infinity, function is now reaching to m. It may be from above or it may be from below, but this is something interesting. As x goes to infinity, positive infinity in this case, function values are reaching to this m. So in such a case, we say y equal m is a horizontal asymptote. The same thing would happen as x goes to minus infinity. So when x goes to either positive infinity or negative infinity, if the function values reach to a finite m, we say y equal is a horizontal asymptote. Horizontal asymptote. You can observe this happens uh, especially for rational functions. So think of function f of x equals x squared plus 1 divided by x times x plus 1. Here both x equal 0 and minus 1 are not in the domain. When you have a rational function like this, first thing you need to check is the degrees of domain and degrees of numerator, polynomial and polynomial in the denominator. Here it is 2 and again 2. Same denominator, same degrees in both numerator and denominator. This one has a horizontal asymptote. What you do is you divide both numerator and denominator by the largest power of x. So this will be 1 plus 1 over x squared, 1 plus 1 over x. When x goes to plus or minus infinity, both 1 over x and 1 over x squared or 1 over any positive power of x goes to 0. They goes to 0. So x goes to plus or minus infinity. If you take the limit, this is as x goes to plus or minus infinity. 1 plus 1 over x squared divided by 1 over 1 plus x. 1 over 1 plus 1 over x, right? This term goes to 0 and this term separately goes to 0. So resulting limit is 1. Right? Now, without looking at any derivative, I can observe some special features of the graph. X equals 0 and x equals -1. So this is x equals 0, x equals -1. Those are not in the domain, and it has a horizontal asymptote. As x goes to plus infinity and minus infinity, function reaches to a finite number. This is a horizontal asymptote. Y equals 1. This is a horizontal asymptote for this function. Also, if you think about this, I can actually do a sign analysis and look at the sign change for this function. So for let's say numbers below -1, x square plus 1 is always positive. No matter what the x value is, it is always positive. For very large negative number like -100, this term is negative, this other term is also negative. So altogether, it is a positive number. Then for numbers between -1 and 0, it's a -1/2. This is negative. X plus 1 is positive. So negative, positive, negative. Altogether, it is a value. For numbers bigger than 0, let's say 5, numerator is positive. Both terms in both factors in the denominator are positive, so it is a positive. So that means below -1, graph lies above the x-axis. Between -1 and 0, graph lies below the x-axis. And after 0, the graph lies above the x-axis. So it will be somewhere here, here, and here. Right? So that's just by analyzing the sign. Now we have a sort of idea how it looks like. If you want now, you can use derivatives. Use derivatives to see the exact behavior of the function. You can compute the derivative of this function using the quotient. Maybe I'll write it as x squared plus x. So this is like u divided by b u prime minus v prime divided by b squared. So x squared plus x times derivative. The numerator is 2x minus x squared plus 1 divided by 2x plus 1 divided by x square x plus 1 square. Let's simplify the numerator. 2x cubed plus 2x square minus 2x cubed plus x square plus 2x cubed x square plus 2x plus 1, then divide by x square 1 square. Now we have some cancellation. This term cancels with this term. 2 square minus x square. So this one cancels with 2. So what we have in the numerator is x square minus 2x minus 1 divided by x square x plus 1 square. We don't have factors for this quadratic term in the numerator. So derivative equals 0 if and only x square minus 2x minus 1 equals 0. You can apply the quadratic formula. And compute the turning points. Minus b plus or minus b square minus 4ac square root divided by 2 times a. Right? 4 plus 4 is 8. Square root of 8 is 2 square root. So this is how it looks like. Now you have two factors. Now let's stop here because this number is not that easy to manipulate. But the point is we can actually continue computation if we want and see the exact turning points. So the graph actually, let me sketch the graph for you at this point. It will look something like this. If you want, you can find the intersection points between it will be something like this. Over here, x coordinate is 1 minus square root 2, and over here, x coordinate is 1 plus square root 2. You can see how I got those 2 points, and also right over here, x coordinate is 1. So right over here, as x goes to minus infinity, function values are decreasing to 1, and as x goes to positive infinity, function values are increasing up to 1. So horizontal asymptote is a kind of important feature for this function, for this graph. Um, Even though I stopped here, I encourage you to go through this computation once again after the class and see whether you can complete this computation. You should look at not only the derivative but also the second derivative, because uh, you see, uh, here in this piece, function has a positive second derivative. It is concave up. In between -1 and 0, it is concave down. And after 0, again function is concave up, while and then it is concave. It looks like it is concave down. So somewhere here we should have an inflection point, a 0 for the second derivative. Uh, it will not, it may not be an easy task to find this point exactly, but we can guess the existence of such a point because of the shape of this function. It should have something, uh, some inflection point somewhere here. And other than that inflection point, we won't have any other. X equals 0 and x equals negative are also kind of inflection points, even though they are not in the domain. In the left-hand side of -1, we have uh, like around -1, we have two different behaviors for the concavity. For the negative, for numbers below -1, it is concave up. For numbers higher than -1, it is concave down. So those 2 points, -1 and 0, are also kind of inflection points. So please continue this computation after the class and see whether you can get the exact picture. So this is what we mean by horizontal asymptotes. Vertical asymptotes, on the other hand, we also have seen those. So something is called a horizontal asymptote. As x goes to x goes to infinity, x goes to plus or minus infinity, function values approach to some finite number. So this is what we call a horizontal asymptote. Vertical asymptotes have the exact same behavior, but it looks like when x goes to some finite number a, when x goes to some finite number a, this is now finite, means it is not infinity. Then function goes to either plus infinity or minus infinity. So how does it look like? Well, let's say this is point A. When x goes to this point over here, function values are now going either positive infinity or negative infinity. So the shape of the graph is something like this, or it may be something like this. In that case, this line y equals k is called the vertical asymptote. Vertical asymptote. We have seen vertical asymptotes. Even this graph has two vertical asymptotes. Here, x equals -1. It's a vertical asymptote because as we approach to -1, function value, like when we approach -1 from the left-hand side, values goes to positive infinity. Also, as we approach -1 from right-hand side, function values goes to negative infinity. So this is a vertical asymptote. And also x equals -0 is a vertical asymptote. So I wanted to display you asymptotes and horizontal asymptotes using an example. That's why I example. But I hope you now have a clear understanding or clear idea about vertical and horizontal asymptotes. The line x equals c is a vertical asymptote for the graph. If we have to see from either negative direction or positive direction, function goes to one of the infinities. It is enough one of these one-sided limits to be infinity. Horizontal asymptotes have like the exact same behavior, but now x and y values get changed. When x goes to plus infinity or minus infinity, function values reach to a finite value. So I have already showed you one of these computations. How can we find the limit of a function like this as x goes to infinity or minus infinity? So usually we compute limit at infinity for rational functions. First thing to note is the largest power of x in the expression, x in the power of x in the given function. Here it is 2. So you divide both numerator and denominator by x squared. 3x squared divided by x squared is 3. Minus x divided by x squared is minus 1 over x. And 2x squared divided by x squared is 2. 1 divided by x squared is 1 over x squared. As x becomes a very large number, if x is very huge, then 1 over x are very small numbers. So you can ignore them. The resulting limit will be just 3 divided by. So here, as x goes to positive infinity, function is reaching to 3 divided by 2. So here we will have a vertical asymptote, right? Vertical asymptote. Because now y values are reaching to a limit. Y equal 3 divided by 2 is a vertical line. Therefore, this is a vertical asymptote. Same thing you can do with this expression. Here what we can think of, what we can observe is the largest power of x is x. So you divide both numerator and denominator by uh, x, then we will have a problem actually. Here we'll get 3 divided by x, and here we will get 2 divided by square root x. As x goes to infinity, both of them, both terms goes to 0, and we are dividing by 0. So we have actually a problem here. So instead of dividing both numerator and denominator by x, you could divide both numerator and denominator by x. That is what I have done in this computation. And without any computation, you can sort of guess what happens. Because when x becomes a very large number, let's try to compare x and of x. The power of x is 1, power of square root of x is 1 half. So x has a larger power than square root of x. So for very large x values, numerator becomes larger and larger compared to the denominator. So something bigger and bigger divided by a relatively small number is still a very big number. We are talking about infinity. It is a huge number. For example, when x is 10 to the power 20, square root of x is roughly 10 to the power 10. Then 10 to the power 20 divided by 10 to the power 10 is again 10 to the power 10. A very huge number. So as a result of this, number goes to infinity as x goes to infinity. So limit at infinity is not a finite number. This function, I can draw the graph of this function, but it won't have any horizontal asymptote. It will not have any horizontal asymptote. Sometimes it is helpful to memorize these limits. I hope you still remember the graph of e to the power x. As x goes to infinity, e to the power x goes to infinity. But as x goes to minus infinity, e to the power x goes to 0. Sometimes it will be helpful for you to memorize these simple limits. And also sometimes it is helpful to memorize this construction called the Tower of Powers. So in the very top of this Tower of Powers, I have put x to the power x. When x goes to infinity, x to the power is the largest growth rate. Yeah, what I have done is I have arranged these functions, these simple functions according to their growth rate. Then below x to the power of x, I have all the exponential functions. 3 to the power x, 2 to the power of x, 5 to the power of x. When I look at their, it depends on the base. 3 is bigger than e. Therefore, 3 to the power x has larger growth rate compared to e to the x. And if I need to put 2 to the power of x, it will be below e to the power of x. And if I want to compare 5 to the power of x, it will be above 3 to the power of x, because 5 is bigger than 3. So likewise, I can think of all the exponential functions sitting in this tower of powers. Once I have taken care of all these exponential functions, I have power functions. For power functions, growth rate depends on the power. For example, x to the power of 100 has a larger growth rate compared to x squared because it has the larger power. And square root of x has a smaller growth rate compared to x. So likewise, I have all these power functions arranged according to their power. Then on the very bottom of this power tower, I have natural log of x. Natural log of x has the smallest growth rate. Um, its growth rate is way below than all these power functions. So how can we use this power tower for computations? We can use this tower powers to compute things like this. Say you want to compute limit as x goes to infinity, ln x over x. Now, this ln x has a smaller growth rate compared to x because ln x is in a level of the tower of powers. So numerator has a small rate, but denominator grows much, much faster. So denominator becomes larger and larger compared to numerator. So we are dividing by a huge number. So result must be 0. And x square and e to the power. Think about this ratio. On the power tower, e to the x is in a higher level compared to x square. Right? Because e to the power x is an exponential function. So denominator gain much faster. So this answer must be 0. For very large x values, x is very large compared to x square. And for something like this, when x goes to infinity, let's see. On the tower of powers, square root of x lies above both x to the power 1 quarter and x to the power 1/8. So here numerator grows faster than. So we are dividing a very large number by something smaller than that. So result must be infinite. So when we take two functions from different levels of power tower, like we saw in these examples, the answer is always either 0 or infinity. 0 or infinity. But if we take two functions from the same level, let me show you something. Like here, when I think about these two, numerator is something like x square, and denominator is again in the level of x square. Both of these functions, if I want to put them, they will be on the same level because both of them have the growth rate of x square. In that case, since I took those functions from the same level, answer won't be 0 or infinity. It will be some other finite limit. It will be some other finite limit. So functions from different levels, ratios of functions from different levels gives us either 0 or infinity, and ratios of functions from the same level will gives us some finite as x goes to infinity. Is it clear so far? Thank you, Ashmita. Okay, so I hope I can move on. Now, look at this example. Find the vertical and horizontal asymptotes for this function. Uh, both in the numerator and denominator, we have two linear functions of x. It means the largest power of x is 1. So as x goes to infinity, we should get some finite value. So there must be a horizontal, non-trivial horizontal asymptote for this function. Even when x equals c, even if the limit is 0, still it is a horizontal asymptote, right? Because 0 is a finite number. So for this function, if I want to draw the graph of this function, I have a non-trivial horizontal asymptote. Y 0. Y equals 0 means x-axis. For very large values, x-axis is a horizontal asymptote. Um, all right. Now, let's think about vertical asymptotes. To have a vertical asymptote, as x goes to a finite number, I should get some infinite limit. When x goes to some finite number, I should get infinite values for the function. That happens for zeros of the denominator. So for vertical asymptotes, we always look zeros of the denominator. These undivisions for the function. Because for any other finite x value, the function gives us finite values, finite y values. X equal 1 or 2 or 4, any other number, this ratio, this rational function gives me some finite value, and it will be some infinite value if x equals 3. So to find vertical asymptotes, we look for the zeros of the denominator. So have two, like x equals 3 as a for the vertical asymptote. Let's see what happens as we approach to 3 from both sides. Let's take below 3. Let's say number 2. If I say x equals 2, I get a negative number. If you want, you can do a sign analysis and see how the sign of this function changes. For numbers below 3, function is negative, and as 3, function value goes to infinity. Negative to some infinite value. So that means it must be negative infinity. For numbers above 3, let's say 4, this ratio is positive. 3, this ratio is positive, and as x 3, this function goes to some infinite value. That means when we go to 3 from the right hand side, function should goes to positive infinity. So at 3, we have a vertical asymptote, and so around a vertical asymptote, function can have different behaviors. In both, it can go to positive infinity, or infinity, or in like for negative and positive one-sided limits, we can get different infinities, and that is what happened here. 3 is a vertical asymptote, and around that we have different behaviors. For the horizontal asymptote, we know there must be a horizontal asymptote because these functions are from the same level of tower of powers. We compute the limit as x goes to infinity. Usually we call it limit at infinity. What happens when x goes to infinity? For that, you divide both numerator and denominator by the highest power of x and set all these reciprocals of powers of x to 0. See, we get 4. Y equal 4 is a horizontal asymptote. So this is how the graph of this function looks like. This horizontal, blue color horizontal line is y equals 4. The red color vertical line is x equals 3. You can in this function in details by looking into its derivative and second derivative. So if you differentiate this function using the quotient rule, uh, you should get something like this: minus 10 minus 3 square. So the function is undefined at 3, the derivative is undefined at 3, therefore 3 is a critical number for the function, but 3 is not in the domain of this function. So even though it is a real number, it doesn't, uh, it won't be a relative maxima or relative minima. Uh, if you think about the derivative, it is minus by some square term. The squares are always non-negative. So this derivative is always negative, except at 3. Because at 3 we can't say anything. Beside 3, it is negative. So derivative is always negative. That means function is always decreasing. See, it starts from a relatively small negative number, then the negative value increases. Negative value increases means function is decreasing. At 3, something interesting happen. Function goes to negative infinity as we approach 3 from the left hand side, and then it jumps to positive infinity. It quickly jumped to positive infinity. Then again it start decreasing and reach to y equals 4. It decreased up to 4. So no relative extreme points. For the concavity, you can take the derivative and differentiate it one time. The second derivative. Second derivative tells us whether it is concave up or down. And see, this is 20 divided by x minus 3, the third power. Second powers are always non-negative, squares are always non-negative, but third powers do change their sign according to whatever you have inside it. So if I pick a number below 3, let's say x equals 0, you are taking the cube of negative 3. It is minus 27. So for numbers below 3, this third power is negative. And as a result, this whole thing is negative. For numbers above 3, like 5 or 7, whatever, this third power is positive and second derivative is always positive. So it is concave down for number below 3 and it is concave up for above 3. You can see it from the graph. Over here, function is looking down. It's open downward. The other hand, this other branch is open upward. It is looking up. So it has two different concavity types. So derivative and second derivative and all the asymptotes. So I have one more example, but I will leave it for you to go through. I want you to go through this example again and see whether you can apply what we learned here to understand the behavior of this function. So, as I said at the very beginning of this course, calculus is studying function, is the study of functions. We started by looking at the domain, then we talked about things like injectivity, invertibility, then we talked about rates of changes, slope of tangents, and now continuity, limits, one-sided limits. We talked about all these and have a very powerful tool, derivatives. By looking at the derivative and the second derivative, we can tell a lot about functions. And today we add one more tool in toolkit, horizontal and vertical asymptotes. So even though we learn this as a tool for sketching graphs, it is really a tool for studying functions. Right. I hope you can see this new node called L'Hopital's rule. So we developed some tools for computing at an early stage of the course because we wanted limits to compute derivatives. So we started from limits and used limits to compute derivatives because definition of the derivative is really a limit expression. So to compute derivatives, we need limits. Now, but this person, L'Hopital's, he was in, I think, somewhere in 1600s or 1700s. No, later than that, 1700s or 1800s. So he found a way for going back. That means he found a way to compute limits using derivatives. So it's a really interesting thing. Once you learn derivatives, you can compute many limits using derivatives. That's what this L'Hopital did. He found a rule. He says, say you have some limit like this, some limit like x goes to c, f of g of x. Let's say you compute limit of f and limit of g separately. So like this, you compute limit of f as x goes to c and limit of g as x goes to c separately. When you do so, let's say your limits become either like both are zero or both are infinities. So resulting expression is like 0 divided by 0 or 80 divided by one of the infinities. These don't have a meaning. We need some number. If it has something like this, those are called indeterminate forms. They are not representing a real number or any other number. We need some real number assigned to this limit. L'Hopital said, if you get one of these things, don't worry, differentiate both numerator and denominator separately, not as a quotient. Differentiate them separately and compute the limit of this differentiated expression, this new expression. So here is something. Let's say you want to find the limit as x goes to 0, sine x divided by x. Then it's substitutes x equals c separately, 0 separately. Sine 0 is 0, x goes to 0, x equals 0. So you get c divided by 0. So the indeterminate form mentioned in this L'Hopital's rule, it is 0 divided by 0. If it is 0 divided by 0, L'Hopital says, don't worry, differentiate numerator and denominator separately. So derivative of sine is cosine, derivative of x is 1. Now evaluate it. When x goes to 0, cosine 0 is 1, denominator now always 1. So 1 divided by 1 is 1. According to the L'Hopital's rule, this limit is really 1. Now you can do it for this expression, like sine 2x divided by 3x. Let's do something different. Let's say x equals to 2, x to the power 7 divided by x to the power 7 minus 128 divided by minus 8. If you compute this, 2 to the power 3 is 8. So we have a problem with the denominator. And also let's compute 2 to the power 7. So the first power is 2 and 4, 8, 16, 32, 64, 128. So 8, 2 to the power 7 is 128. Again, we have a problem with the numerator because now this is an indeterminate form, 0 divided by 0. So the L'Hopital says, don't worry, if this is the case, differentiate it. So you differentiate both numerator and denominator separately. X to the power 7 minus 128. Derivative of 128 is 0. Derivative of x to the power 7 is 7x to the power 6. It's the power. Then derivative of x to the third minus 8 is 3x squared. So the result is something simpler. In fact, you can compute it, cancel x squared terms, 2x squared terms from numerator and denominator. Result will be x goes to 2, 7x to the fourth power divided by 3. At this point, this is not an indeterminate form anymore. You can simply substitute x equals 2. So the L'Hopital's way of computing limits. If you imagine these two, this limit with our earlier knowledge on limits, we would want to factor numerator and denominator and compute limits. But factor is something with x to the third power and third power. It's not impossible, but it is like inconvenient. It will be messy and it will take some time. So it is computationally, it is a little bit cost. So you see, we can compute indeterminate forms using L'Hopital's rule very easily. Now we can apply the L'Hopital's rule for not only for x goes to some finite limit. We can do the same when x goes to infinity. When x goes to infinity, still the same rule applies. For example, let's say we want to compute x goes to infinity, limit of this expression. We now have a very efficient way of computing this limit, tower of powers. Here, these two are from the same level of tower of powers, x squared. We can divide both numerator and denominator by x and do the computation, do whatever we did in the earlier session. But the L'Hopital's rule gives us a shortcut. We can obtain the same limit very easily. So take this and directly substitute x infinity and see what happens. When you do so, you get infinity divided one of the indeterminate forms. So don't worry, differentiate both numerator and denominator. When I differentiate 3x squared plus 2, I get 6x. Uh, then derivative of 4x square plus 7x is 8x plus 7. So by differentiate separately, I mean do not differentiate this as a quotient. Do not apply the quotient rule. Differentiate numerator and denominator separately. Uh, Okay, now we have a different expression, different function to compute the limit. But L'Hopital's, yes, we are getting a separate, a different function, but still at the limit, they will have the same value. So limit as x goes to infinity of this function is same as limit of this function at infinity. But now still we have not solved the problem completely. We have reduced the powers, but still this is infinity divided by infinity. If I substitute x equal infinity, 6x is infinity and 8x plus 7 is still infinity. So still this is an indeterminate form and indeterminate form infinity by infinity. So still the L'Hopital's rule. So take the same function and differentiate numerator and denominator separate. Derivative of 6x is 6. Derivative of 8x plus 7 is 8. Now I get something free x terms. Limit as x goes to 6 divided by 8. 6 divided by 8 is a finite number. It has nothing to do with x. It doesn't come. It doesn't care about limits because it is a number. It is not a like a function depends on x anymore. So as x goes to infinity, function value limit the value of this number is still 6 divided by. So what does it says? Limit of this function is 6 divided by 8 at infinity. By the way, 6 divided by 8 is same as 3 divided by 4. They of these leading coefficients. Mhm. Again, we can find the limit of this function if you want using the L'Hopital's rule. Angle of uh, tower of powers. This is a very simple limit term because natural log is in the lowest level of tower of power. So this has the smallest growth rate. Cubic root of x has a larger growth rate compared to natural log. Denominator is growing very quickly. So what happens is the limit should be 0. Again, if you want, you can apply the L'Hopital's rule. Uh, Maybe a few times if you want to apply the L'Hopital's rule, always you need an indeterminate form. You need 0 divided by 0, infinity divided by infinity. Hmm? Uh, L'Hopital's rule is especially helpful for complicated functions like can you quickly solve this limit problem? Compute limit x goes to 0, x minus sin x divided by x square using the L'Hopital's rule. I can give you 2 minutes. All right. Uh, yeah, most of you got it. Let me see. Mm, yeah, you got it correct. The answer should be 1 over 6. Um, However, you cannot use the L'Hopital's rule if the function is not an indeterminate form. For example, let's say 1 minus cosine x divided by sec x. When x goes to 0, uh, the answer is when x goes to 0, value of cosine 0 is 1, therefore value of secant 0 is also 1. So the real answer is 1 minus 1 divided by 1. That means 0 divided by 1. So answer is 0. You cannot simply, like, this is not an indeterminate form. This is a genuine real number. Now, you can take a pencil and a paper and see what happens when you apply the L'Hopital's rule blindly for this example. You will get a completely different answer, and you it is a completely wrong answer. To get the correct answer, you need to apply the L'Hopital's rule only if you have an indeterminate form. You need either 0 by 0 or some infinity divided by some other infinity. There are other indeterminate forms like 0 times infinity, because 0 times anything is 0, and infinity is so huge that infinity times anything is infinity. So there is a problem of assigning a real value for this. Then infinity minus infinity, because if you add any finite number to infinity, that is still infinity. It's like infinity plus some n equals infinity. So the difference between two infinities would be, you can assign any finite number. Like you can choose a correct answer for this. Same thing is true for these other numbers. Uh, so if you have something like this, 0 divided like one of these infinities, you can still apply the L'Hopital's rule. What you do is you convert these indeterminate forms to form 0 divided by 0 or infinity divided by infinity form. Okay. Always you need to convert these type of indeterminate forms to 0 divided by 0 or infinity divided by infinity form. For example, let's say x goes to 0, x ln x. When x goes to 0, x is 0. As x goes to 0, natural log of x, it has a problem. You cannot go to 0. The domain of natural log is always positive real numbers, not negative, not even 0. So here this must be actually one-sided limit. X should go to 0 from positive direction, from right-hand side. So in that case, natural log goes to negative infinity. So 0 times minus infinity, an indeterminate form. So you cannot directly differentiate x and ln x, because to apply the L'Hopital's, we need 0 by 0 or infinity by infinity. So let's take this expression and rewrite it like ln x divided by 1 over x, because multiplying by x is same as dividing by 1 over x. Now it is So it has this indeterminate form, C infinity by infinity. So you can apply the L'Hopital's for this function, not for the initial function, but for this new function. Let's differentiate denominator and numerator separately. You'll get 1 over x for ln x and negative 1 over x square for 1 over x. After applying the L'Hopital's, simplify it. When you simplify, you can easily simplify this to get minus x. As x goes to 0, minus x goes to 0. So the actual limit is 0. 0 is a genuine real number, a finite, nice real number. So this is your answer. As x goes to 0, function up to 0. Here is another example, but I will skip it because I want to move to the next section quickly. Um, Here are some other examples. You should look at these examples and try to see you can convert one of these indeterminate forms to 0 by 0 or infinity by infinity. Always you need to convert these indeterminate forms to 0 by 0, especially if it has powers. Like if the indeterminate form is 1 to the power 0 to the power 0 or infinity to the power 0, need logarithms, because once you take a log of an exponential becomes the power becomes a coefficient. Power becomes a you can bring the power to front and make it a regular function. So for these things, you need to take logarithms. Please go through examples provided in the note. All right. I need to quickly finish this section in the today's class. This is one of the main aspect of differentiation, main application of uh, derivatives, optimizing. How to perform a task by optimizing the result or by optimally using the available resources. Let me show you and let's discuss some examples. Optimization is the process of finding the maximum or a minimum of a function for a certain process. We have already seen this. Let's say this is a nice example. A farmer has uh, a farmer wants to build a fence around his farmland. He has enough material to uh, build a fence of 2,400 feet long, and he wants it to be a rectangular, and at the same time he wants it to uh, make it so build it so that one edge is a river. So he has this farmland, and at the end of his farmland he has a river. There is a river. Now he wants to build a fence covering his farmland, maybe to protect from animals. Hmm. He only has material, fancy material for 2,400 feet long. Hmm. Now, let's say his farmland is huge, so he has enough land, but not enough material to cover the whole thing. So he wants to cover a part of his farmland, maybe to raise some animal here, maybe to grow some plants. I don't know. So you see, now you can arrange this rectangular pen in various different shapes. You can choose one, X and Y to be any lengths. As long as X times Y is uh, like as long as the perimeter covered by this fencing material is 100, 2400, 2400, he can do it. Now the problem is how to maximize the area. So he don't have enough fencing material. Uh, with the available material, he wants to maximize the area covered by uh, fence. So he wants to optimize or maximize the area. Now, give me a second. I want to plug my computer. So he wants to maximize the area. Area is X times Y. Area depends on two parameters, two variables, X and Y. But X and Y are not independent from each other because length of this whole fence must be 2400. So 2x, so 2y plus x equals 2400. So we want to maximize the area function subject to this restriction, subject to this constraint. So what we can do is we can use derivatives for the area function if we have it as a function of a single variable. If we have a function of a single variable, we can differentiate it. So we can remove y from these two expression and make it to a single expression of x. So find y in terms of x, substitute it into the first formula. When you do so, you get area equals 1200x minus x squared divided by 2. I'm not going to explain this simple algebra. You can do it by yourself. And so area is a function of x. Area is a function of x. Whenever you have a function, you always need to think about its domain. You are going to maximize something, area as a function of x. If it is a function of x, what are the possible values for x? Always you need to think about it. Okay? Because otherwise you will run into problems. So the smallest possible, you can make x as small as you want by increasing the y value. Even you can set y to be 0. If y equals 0, so when you can set x equal to 0. When x equals 0, y will be 1200 according to the constraint, but at that point it is like a very thin long rectangle. Area is 0. So the smallest possible x value is 0. X cannot be negative because it is a length. The smallest possible x value is 0. And the largest possible x value is 2,400. If x is 2,400, y will be 0. Okay, it's like a very flat rectangle. It will be stretched along the like a river. Uh, yeah. Uh, Again, in that case, area will be 0. So x can take any value between 0 and 2,400, not beyond those 2 points. At the end points, area is 0. Both points gives you 0. Now, that should remind you something. The Rolle's theorem. You have a function defined on a bounded closed interval, and at the end points, you have the same function value. Function takes the same value. So that the Rolle's theorem says in such a case, there is a point in the interval for which derivative is 0. That means the function has a local maximum or a local minimum in that interval. Now, we have a function to be optimized. Area as a function of x, and we know the domain. Let's take the function and differentiate it. When you differentiate, it's a very simple derivative. Derivative of 1,200 x is 1,200 minus derivative of half xy is half times 2x, it's just x. So derivative is 0 if x is 102,000. So 1,200. 1,200. Okay. So at this point, we have an optimum value for the area or extreme value, local extreme value for the area. It could be a maximum, it could be a minimum. We don't know. We need to check whether it is a maximum or a minimum. By the critical number, by the extreme value theorem, we know, sorry, by the extreme value theorem, we know it has the extreme value, or we can also use, by Rolle's theorem, it has a critical number, and the critical number theorem says local extremes are usually critical numbers or endpoints of the domain. At the endpoints, area is always 0. At this new candidate for the extreme value, this critical number, area is, you can compute the area using this formula. It turns out to be 720,000. You can look at the sign changes. Before 120,000, derivative is positive, right? If x is below 120,000, derivative is positive. After 120,000, derivative is negative. If x is bigger than 120,200, yeah, if x is below 1,200, derivative is positive. That means function is increasing. And after 1,200, derivative is negative. That means function is decreasing. So up to 1,200, function is increasing and hits a local extreme, then it decreases. That means increasing, flat, decreasing means a maximum. This is a local maximum for the function. Or you could differentiate this twice. Derivative, the second derivative is 1. Negative 1 means the graph is concave down. So always the function is concave down. Concave down means it is looking downward, and therefore it must have a local maximum at the critical point. Right? Mm. So this is how you solve an optimization problem using derivatives. Always optimization problems are, most of the optimization problems are word problems. If you are given something like this, you need to identify the function that you need to maximize. Here, they ask what dimensions gives the greatest area. That means you need area as a function of its dimensions. Okay? Area as a function of its dimensions. According to this problem, you computed x to be 1200. When x is 1200, you can substitute it here. Uh, y should be 600, right? Should be 600. So that those are the dimensions giving us the greatest area. So first of all, you need to identify the function and the variable. Functions and variables. If there are multiples, uh, we cannot use derivatives to optimize a function with more than one variable. So there must be a way to eliminate these additional variables. So we must have some restrictions. So here the farmer has only fencing like materials only for 2,400 long length. So that is a restriction. And also he wants it to be a rectangular pen. So those kind of things should be there to make a single variable function. So identify the function, identify the variables, identify the constant. Once you have all these things in place, domain of the function, check the derivative. Also check the second derivative. Sometimes you might find it some interesting things. Also, according to some, depending on the problem, you might want to look at asymptotes. Also, you might want to look at some limits. It all depends on the function. So, look at the problem, build the function, see what you want to do, and now you have tools available for things. You just need to come up with the right tool and analyze it properly. Right. Let's look at another example. Design a 1 liter oil can shaped like a right circular cylinder. What dimensions will use the material? Okay, let's see. So we need an oil can um, of the shape of a right circular cylinder. So base is a circle, and volume depends on two parameters: radius of the base and height. You cannot arbitrarily change radius and height because we need it to have a certain volume. Okay, so there is a restriction. Volume is a 1 liter. So we have two variables R and H. We cannot arbitrarily change them because volume must be 1 liter. And so there are different shapes, different R and H values for the same shape, for the same volume. Because while you're increasing radius, you can decrease the height without changing the volume. Hmm? Now, uh, the actual problem is what dimension will use the least material, least amount of material. Uh-huh. So we need a function for the amount of material. Amount of material means the surface area. So we want to minimize the surface area while keeping the same volume. So first step is to draw a picture, identify the given parameters. We can do all relevant quantities, height and radius. Uh, so then find a formula for the quantity to be optimized. Here we need to minimize the surface area. In last problem, we wanted to maximize an area. This problem, we want to minimize an area. Okay. It may be um, costly to make this can. Uh, I don't know. Okay. So surface area. Uh, so we need to cover the bottom and this curved surface, area of the bottom and top. Uh, area of the top and bottom consists of two circles, circular disc. So 2 times pi r square plus area of the curved region is 2 pi r times h. They have not said anything about the top and bottom. So we are, since they have not said that this is an open can, we should assume that it is a closed can and we should take both top and bottom into account. All right. So this is the total surface area, both top and bottom and the curved area. Then we are given a constraint. Volume is a constant. It is 1000 cubic centimeters. Volume is pi r square h. Okay. Let's think about this for a second. We have area as a function of two variables, h, both of them present in this expression. So to use derivatives, we need to remove one of the variables. It could be r or h, but by looking at the expression, I think it would be wise to remove h. Easier to remove h because we have it. R square and r prime. So it's better to keep this simple, better to remove this simple h term. So volume is pi r square h, it is simple 1000. So h is 1000 divided by pi r square. Take this and substitute it in the expression we obtained for the surface area. So you get this function 2 pi r square plus 2 pi r square plus 2000 divided by r. Of what dimensions? What are the dimensions? What are the possible values for h? We can make it to 0, like we can make it smaller as much as we want. Then the cross section, a cross section will be very small, but by taking a very large height, like a very tiny cylindrical tube, still we can get the same volume, right? So the smallest value that R can reach is 0, but not 0 because you see here R is in the denominator, so R cannot be 0. If R is 0, there won't be a can and there won't be a volume. At the same time, you can make it as large as possible. Uh, mm, you can make R as large as you want by taking a very small height. This will be very uh, short and flat, spread across. So this is the domain 0 to infinity. R can take any positive real number. All right. So this is the domain. It is not that helpful. But this is an open interval, not a bounded closed interval. It goes to infinity. Now take this expression and differentiate it. Uh, so I'm not going to explain the derivative, differentiation part because the function is really simple. Uh, to have extreme values, derivative must be 0. That's how we find critical numbers. Set the derivative equals 0, find zeros of the derivative. Using the exact value is cubic root of 500 divided by pi. Using a calculator if you want, you can approximate this value. It is roughly 5.42 centimeters. You can go back and substitute it for height h. Height h is roughly like 10.84 centimeters. If r is below this number, for a smaller r value, you can say, let's say, r equals 1. If r equals 1, this is like 4 pi minus 2000. Pi is 3 point something. So 4 pi means 12 point something. 12 point something minus 2000 is a negative number. So for small r values, derivative is negative. For a very large r value, 2000 divided by r twice, very small, and 4 pi r will be large. So a small number subtracted from a large number is positive. So derivative is positive for numbers bigger than this particular value. So derivative, at first derivative is negative, so function is decreasing. And at this point, 5.42, function hits a critical point, then it starts increasing. So decrease, a flat point, and increase. So that must be, this point must be a local minimum for area function. Or you could use the second derivative. Take this derivative and differentiate it one more time. And second derivative is 4 pi minus 2000 divided by r to the third power. For any positive r value, this is positive. Second derivative is positive. So function is going up. It is looking upward. So it has a local minimum at this particular point. So you should build, you should construct this oil can with this radius and this height. And when you do so, its area will be minimum and the volume will be 1 liter. Volume will be a single liter. So that is another optimization problem. So here is a variant of the same problem. The same problem, but now it has changed by a little bit. Design a one you can shape like a right circular cylinder with the condition that material for top and bottom costs $5 per single centimeter and the curved side costs $2 per square centimeter. Find the dimensions that minimize the cost. Now, top and bottom and the curved area uh, created by different materials. So they have different uh, costs. So that this time you are not minimizing the total surface area, you're minimizing the cost. This time you need to write an expression for the total cost and minimize that one, minimize the cost function, not the total surface area. Still we have a constraint. Constraint is volume. Volume must be a single liter. So top and bottom cost $5 per square centimeter. Therefore, for the total area is pi r square, and pi r square multiplied by 5 is the cost to make the top lid. For the bottom, it is the same. So 5 times 2 circles, pi r square, plus for the curved side, it costs $2 per single square meter. So 2 times 2 pi r square h. So this is the cost function. And in the cost function, two variables, r and h. Again, remove h using the volume constraint, volume condition. This time you're optimizing a different function. Still, it has something to do with the area, but it is a different function. You're minimizing the total cost function. So you will get different dimensions. Yeah, I will leave it from here for you to study. We are almost done actually. Huh? Last problem is also something somewhat interesting. It is about some marine algae and some biochemical process. So to it. So this is the end of 0.6. This is the end of our discussion on applications of derivatives. Next time we'll discuss something else. We still have to do, and it is a relatively short chapter, right? So yesterday I asked you to submit an in-class assignment. Most of you have submitted it. Some people, for some people, it took longer than I expected. Some people have submitted it 2-3 minutes after the deadline. It won't be a problem. For example, if you submitted within 30 minutes of the deadline, it won't be a problem. Okay. Otherwise, I'll give you some marks. All right. I will email if I have something to share with you. We need to have a mid-semester exam, but even in the university, our semester is supposed to end by this month. So I'm kind of busy with the other classes too. So I'm not planning to have a mid-semester exam within November. At the same time, I want to give you some time to practice. I want to give some assignments for you before the mid-semester exam. So it will be like middle of December or near the end of December. Also, I will look at whether we can have some discussion classes after you come to the university before the uh, um, before the end semester exam. Hmm? All right. So that's it. That's all for today. If you have any question, I can. I'm happy to answer. Otherwise, uh, you can leave. Yep. Have a nice day.